Module 1, Lecture B, Variables and Expressions. By the end of this lecture, you will be able to create variables that represent civil engineering quantities with meaningful names, use arithmetic expressions and built-in functions to compute engineering values, and apply basic type awareness to avoid common calculation errors. Engineering variables, meaningful variable names. In civil engineering, clear names for values help make calculations understandable and reliable. A name should indicate the physical quantity, its context, and its units, such as a beam length or concrete density. Vague names can cause confusion as projects expand or when others review the work. Descriptive naming supports transparency, professional communication, and quality control. In engineering, clear names for quantities are essential because the same number can represent very different things, such as a dimension or a load. Precise naming helps prevent mix-ups between related values like wall height and embedment depth, or rainfall intensity and peak discharge. It also makes calculations easier to check and revise, reducing the chance of hidden errors. Use clear, concise, and consistent names for values in engineering projects. Names should show the relevant context, such as the dimension being described or whether a load is existing or proposed. This makes calculations easier to understand, especially in collaborative work, and helps maintain clarity and traceability. Python code. Meaningful variable names. Use meaningful names in engineering calculations to make the work easier to understand and check. Names should clearly describe the physical quantities they represent, and including units can help prevent confusion during calculations. The beam is defined using metric dimensions: a length of 6 meters, a width of 0.3 meters, and a depth of 0.5 meters. These measurements describe its physical size and provide the basis for later calculations such as volume and mass. To find the mass of a concrete beam, use a concrete density of 2,400 kilograms per cubic meter. First, calculate the beam's volume by multiplying its length, width, and depth. Then, multiply that volume by the density to get the beam's mass in kilograms, which helps describe its structural properties. The road dimensions are set as 1,200 feet long and 24 feet wide, with an asphalt layer 4 inches thick. These measurements define the key inputs needed to calculate the total asphalt volume, after converting the thickness from inches to feet. The code first converts asphalt thickness from inches to feet, so all measurements use the same units. It then finds the pavement volume by multiplying the road length, width, and converted thickness. The result is the total volume in cubic feet, which can be used for material estimates or related engineering calculations. The output reports the beam volume, beam mass, and pavement volume, using rounding to keep the numbers easy to read. Each value is shown with appropriate units and a sensible number of decimal places. The final message highlights the importance of clear variable names that describe the quantity, context, and units used in calculations. This script computes a concrete beam's volume and mass, then calculates the volume of an asphalt pavement. It uses descriptive names that include the quantity, context, and units, which helps make the calculations easier to understand and less error-prone. The beam is measured in meters, while the pavement uses feet, with asphalt thickness converted from inches to feet before finding volume. Meaningful variable names. In civil engineering, clear names for stored values help make calculations easier to understand and check. Descriptive names show what a quantity represents, such as a beam distance or soil property, while vague names can cause confusion. Good naming preserves the engineer's reasoning and reduces the risk of misinterpretation later. In civil engineering, clear names for quantities help prevent mistakes when similar values mean different things. A name should identify both the object and the property, such as separating pavement depth from asphalt thickness or design load from other bridge loads. Good naming makes relationships between quantities clear before calculations begin. In civil engineering, clear and consistent naming supports teamwork and quality control. Names should use standard engineering terms so digital information connects easily with drawings, reports, and calculations. They should be short but meaningful, giving enough context to avoid confusion between similar items or project stages. Python code. Meaningful variable names. Use meaningful names for stored values in engineering calculations so they clearly represent real quantities. Clear labels make work easier to review and help prevent design errors. The beam is described using clear dimension values: a 6-meter span, a 3.5-meter slab width, and a 0.18-meter slab thickness. Using descriptive names for these values makes the design information easier to understand and helps reduce mistakes during review. Concrete density is taken as 24 kilonewtons per cubic meter. The slab volume is found by multiplying its width, span, and thickness. Then the slab weight is calculated by multiplying that volume by the concrete unit weight. This gives the total slab weight needed for engineering assessment. This example uses vague variable names to show why clear naming matters in code. The values represent a beam span of 6 meters, a slab width of 3.5 meters, and a slab thickness of 0.18 meters. Because the names give no context, it's harder to understand what the numbers mean. The code compares unclear and meaningful variable names while calculating a slab's weight from its dimensions and the concrete unit weight. Both results are rounded to 2 decimal places, showing that clear names make the calculation easier to understand without changing the outcome. The code demonstrates why clear variable names matter in engineering calculations. It prints the slab volume in cubic meters and the slab weight in kilonewtons, with sensible rounding and units to make the results easy to understand. It also shows a less clear calculation to contrast the effect of vague naming. The main lesson is to use descriptive names for engineering quantities, so code is more readable and results are easier to interpret. This example shows why clear variable names matter in engineering calculations. It computes a concrete slab's volume from its dimensions, then finds its weight using the concrete's unit weight. A version with vague names gives the same result, but is harder to understand and easier to misuse. Descriptive naming makes the calculation clearer, safer, and easier to check. Meaningful variable names. In civil engineering computations, meaningful names help connect program values to real-world quantities like beam span or concrete strength. Clear names reduce guesswork and make analyses easier to review and maintain, especially when results affect design decisions, costs, and safety checks. A short, vague name may save time at first, but it can create confusion later. In engineering work, variable names should clearly describe both the object and the property being measured. This is especially important when similar quantities appear in the same project, such as different dimensions, flows, or traffic measures. Specific names like peak stormwater flow or daily traffic volume reduce ambiguity and help keep the engineering meaning clear throughout calculations. Meaningful names in civil engineering calculations make work clearer safer, and easier to review. Clear, concise names help others understand the logic, notice assumptions, and catch mistakes later. They should fit the engineering context and include units when needed to prevent serious errors. Python code, meaningful variable names. Use clear names for engineering quantities so calculations are easier to understand. Names should show what each quantity means, and when helpful, they can include the units. The example defines three clearly named quantities for a beam: a 6-meter span, concrete strength of 30 megapascals, and a uniform load of 12 kilonewtons per meter. Including both the meaning and units in each name makes the values easier to understand and helps the code stay readable. The maximum bending moment for a simply supported beam with a uniform load is found by multiplying the load per meter by the square of the beam span, then dividing by 8. This gives the result in kilonewton meters. Using clear descriptive names for the load and span makes the calculation easier to read and understand. The example assigns two numerical values and uses them to compute a third value by multiplying the second value by the square of the first, then dividing by 8. Although the calculation is valid, the vague variable names make its purpose hard to understand. The main point is that meaningful names help clarify the intent and context of a calculation. The code displays key beam design values in a clear format: the span in meters, the concrete strength in megapascals, and the uniform load in kilonewtons per meter. Descriptive names make each printed engineering quantity easy to understand and interpret. The example prints a maximum moment in kilonewton meters using both descriptive and vague variable names. Comparing the two shows that clear names make engineering calculations easier to understand and maintain. The script ends by reminding us to use clear, descriptive variable names. Good names should indicate what is being measured, the relevant context, and the units. This makes code easier to understand and maintain, especially when working with precise engineering calculations. This script shows why meaningful variable names matter in engineering calculations. It computes the maximum moment for a beam by using clear names for values such as beam span, concrete strength, and uniform load, then compares this with the same calculation using vague names. The example highlights that descriptive names make the purpose, quantity, location, and units of each value easier to understand. Engineering expressions, arithmetic calculations. Arithmetic calculations are essential in engineering programming because they turn data and assumptions into useful results. In civil engineering, they support tasks such as combining measurements, applying loads to areas, and estimating time from rates. Programming makes these calculations more efficient, consistent, and easier to check or adjust than doing them by hand or in spreadsheets. Order of operations is essential for accurate calculations because multiplication, division, powers, addition, and subtraction must be applied in the correct order. In engineering, unclear grouping can change results, even in important calculations like loads or safety margins. Using parentheses makes the intended order clear and helps others understand and check your work later. When building arithmetic expressions, focus on what the quantities physically represent, not just the mechanics of calculation. Check that units and scale are consistent, since operations only make sense when the values are compatible, such as using matching dimensions to compute area or volume. Many mistakes come from poorly prepared values rather than difficult operators. The goal is to make calculations accurately reflect the engineering problem so they support better decisions. Python code, arithmetic calculations. Arithmetic expressions convert measurements into useful engineering quantities. Clear use of parentheses makes calculations easier to understand and review, while consistent units help prevent common engineering errors. The code defines the main road measurements: a length of 125 meters, a width of 7.5 meters, and an asphalt thickness of 12 centimeters. Clear naming helps make these values easy to understand and maintain. To find the asphalt volume, first convert the asphalt thickness from centimeters to meters so the units match. Then multiply the road length by its width to get the pavement area. Finally, multiply that area by the thickness in meters to get the total asphalt needed in cubic meters. The total asphalt cost combines a variable material cost with a fixed mobilization cost. Multiply the asphalt volume by $145 per cubic meter, then add $2,500 for mobilization. The built-in round function is used to make engineering results easier to read. It rounds the pavement area, asphalt volume, and total cost to 2 decimal places, giving clear and professional measurements. This keeps the results precise enough for engineering use while making them simple to interpret. The crew can place 32 cubic meters of asphalt per day. To estimate the schedule, divide the total asphalt volume by this daily productivity to get the required time in days. Since any leftover fraction still requires another workday, round down to the nearest whole day and add 1, ensuring enough full days are planned to finish the job. The output reports the key paving estimates in a readable format: pavement area in square meters, asphalt volume in cubic meters, total cost in dollars, and crew duration in days. Values are rounded for clarity and precision, while the planned work schedule rounds the duration up to whole days, so the crew is booked for complete work days. This script estimates the materials, cost, and schedule for paving a road. It converts asphalt thickness to meters, calculates pavement area and asphalt volume, then combines volume-based pricing with a fixed mobilization cost. It also estimates crew duration from productivity and rounds up to plan full work days. The final output gives the area, volume, total cost, exact duration, and planned days in a concise format. Built-in functions. Python's built-in functions are ready-made tools that make calculations clearer and more efficient. In engineering, they help with tasks such as finding maximum loads, rounding measurements, summarizing data, and checking result sizes. This supports reliable design decisions, such as identifying the largest beam load or counting survey readings. Built-in functions help civil engineers turn raw data into useful values by quickly finding totals, extremes, rounded results, and absolute differences. These tools support practical analysis, such as summarizing material strengths, rainfall data, or excavation volumes at an appropriate level of precision. Used well, they make calculations clearer, more readable, and better aligned with professional engineering practice. Built-in functions can make calculations faster and reduce repetitive work, but engineers still need to judge whether a function matches the problem. Choosing a maximum or an average depends on what the result is meant to represent, and rounding should usually wait until final reporting to avoid unnecessary error. A disciplined workflow uses Python for efficient computation, while the engineer checks the inputs, understands the outputs, and interprets the results in context. Python code, built-in functions. Built-in functions can make civil engineering calculations faster and more reliable. They help summarize small sets of measurements quickly, while type checks reduce the risk of calculation errors. We store concrete strength measurements in megapascals as a list of sample values. This makes the data easy to analyze for common engineering tasks, such as calculating averages or finding the maximum strength. A set of 4 slab thickness measurements in inches is stored for later engineering analysis. The readings are 5.9, 6.1, 5.8, and 6.0, and they will be used for summaries and validation checks. Before analyzing the datasets, we first confirm that both contain data. This means checking that the concrete strength values and slab thickness readings are not empty. If both lists have at least one entry, the data is ready for calculations and summaries. Use the maximum function to identify the strongest concrete sample, the minimum function to find the thinnest slab measurement, and the length function to count how many thickness readings are available for analysis. Average concrete strength and slab thickness are found by adding all measurements in each group and dividing by the number of measurements. These mean values summarize strength in megapascals and thickness in inches, helping assess overall material performance and construction consistency. Set the target slab thickness at 6 inches, then measure how far the average slab thickness is from that target. Use the absolute difference so the deviation is always positive, whether the average thickness is above or below 6 inches. Round the average strength to 1 decimal place to keep the reported value concise and easy to present. Round the thickness deviation to 2 decimal places so it remains precise while still being clear for reports or discussion. Before reporting results, the code checks the data types of the reported strength and the reading count. It does this by identifying each value's type and converting that type name into text. This helps confirm the values are in the expected format and reduces the chance of errors when they are used or displayed later. The output first confirms that the datasets contain data, then summarizes key measurements: maximum and average concrete strength, minimum slab thickness, the number of thickness readings, and the average deviation from the target thickness. These values help describe material performance and measurement consistency. It also checks the data types for the reported strength and reading count to help catch type-related issues before further processing. This script gives a quick engineering summary from concrete strength and slab thickness data. It first confirms that both datasets contain values, then reports key results such as the maximum and average strength, the minimum and average thickness, and the number of thickness readings. It also compares the average thickness with a target value, rounds results for clarity, and checks the data types of selected outputs before displaying them. Using built-in functions. Python's built-in functions help engineers handle common calculation tasks, such as finding maximum or minimum values, rounding results, and converting data types. They make work like checking beam deflections or survey depths faster, clearer, and less error-prone. This supports accurate results for design decisions, cost estimates, and field judgments. To use built-in functions well, you need to understand what inputs they take and what results they return. Some functions operate on one value, while others compare several values, such as loads or travel times, to find the controlling result. Rounding is also important because it presents engineering results at a practical level of precision. Knowing these details makes calculations more efficient, accurate, and meaningful. Built-in functions can speed up calculations, but engineers must still judge whether the results make sense. Accuracy depends on choices like keeping full precision until the final result, using relevant and reliable data, and maintaining clear names and consistent units. These tools are most valuable when their outputs are interpreted thoughtfully to answer practical engineering questions. Python code using built-in functions. Built-in functions make engineering calculations easier, while meaningful variables help keep units clear. Rounding final results makes reports more readable. A list is created to store 4 beam deflection measurements in millimeters. These values show how much the beams bend under load, keeping the data organized for later analysis, such as comparisons or finding the maximum deflection. A list stores several excavation depths in feet: 6.2, 5.7, 6.8, and 6.1. These measurements represent depths from different excavation points and can be used later for analysis or comparison. To find the largest beam deflection in a set of millimeter measurements, use the max function to identify the highest value. This maximum is the governing deflection and helps assess the beam's most significant response for structural analysis and decisions. To find the shallowest excavation point, use the minimum function on the list of depth measurements. It returns the smallest depth value, which can then be saved and used later in calculations or reports. The observed elevation is 102.36 meters, while the design elevation is 102.50 meters. Comparing these values shows how the measured site height differs from the planned engineering height, helping identify any deviation from the design. To compare observed and design elevations, use the absolute difference between them. This gives the size of the deviation without considering whether the observed elevation is higher or lower. In engineering, this non-negative value is often the most useful measure because it focuses on how large the difference is. The slab dimensions are set as 12 meters long, 4.5 meters wide, and 0.18 meters thick. These values provide the basis for calculating the required concrete volume. To find the concrete volume, multiply the slab's length, width, and thickness in meters to get cubic meters. Then round the result to 2 decimal places so it is clear and practical for engineering reports. The output reports 4 key construction measurements in readable units: maximum deflection in millimeters, minimum excavation depth in feet, elevation deviation rounded to 3 decimal places, and concrete volume rounded to 2 decimal places. Together, these values give a concise summary of structural movement, excavation depth, elevation accuracy, and slab material quantity. This Python script uses built-in tools to produce key engineering results. It finds the largest beam deflection, the shallowest excavation depth, the positive difference between observed and design elevations, and the slab concrete volume from its dimensions. The final output reports these values with practical rounding for clear engineering use. Built-in functions. Rounding results. Rounding can make calculations look cleaner, but it also removes information and can hide assumptions about precision. In engineering work, keep the most precise values available throughout the calculation process, especially when results come from measurements or conversions. Round only at the end when presenting or documenting the final result to improve clarity without introducing avoidable errors. When rounding results to a set number of decimal places, remember that computers store decimals as approximate floating point values. Tiny hidden differences can affect rounding, especially when a value is close to a cutoff point. So if a rounded result differs from a quick mental estimate, it may be due to the exact stored value rather than an error. In civil engineering, rounding is a deliberate decision because it can affect safety, cost, and compliance. Material quantities may be rounded up to ensure enough supply, while report values may simply be rounded to a suitable number of decimal places. Engineers must consider the type and purpose of each number so results stay clear, consistent, and reliable. Python code, rounding results. Rounding helps make engineering results clear, but it should be done at the right time. Keep full precision during intermediate calculations, and round only when presenting final results. The concrete slab is defined by its length, width, and depth: 8 meters, 3.5 meters, and 0.127 meters. Storing these measurements as precise decimal values supports an accurate volume calculation. To find the concrete slab's exact volume, multiply its length, width, and depth in meters. This gives the volume in cubic meters, which should be calculated precisely before any rounding is used for reporting. The calculated volume of the concrete slab is rounded to 2 decimal places for reporting. This makes the final value clearer, more readable, and consistent for communication. The program prints the concrete slab volume in 2 forms: a precise value for accurate engineering calculations, and a version rounded to 2 decimal places for reports. This keeps the underlying calculation exact while making the reported result easier to read. Set the truck capacity to 5 cubic meters, meaning each truck can carry that volume. Use a safety factor of 1.1 to add a buffer for unexpected variation when estimating the number of trucks needed. To estimate the trucks needed, calculate the concrete volume with a safety margin, then divide that total by 1 truck's capacity. The result is the exact truck count as a decimal, which should be rounded up to ensure enough concrete can be delivered. Python's math module provides functions for mathematical calculations, including rounding numbers up. This is important when finding how many trucks are needed, because any partial load still requires a whole truck. To find the required number of trucks, use the ceiling function to round the calculated need up to the next whole truck. This avoids fractional trucks and ensures there is enough capacity for the full volume, including any safety margin. The calculated number of trucks is first shown rounded to 3 decimal places, giving a precise estimate of the need. Then the final truck count is rounded up for ordering, because a fraction of a truck cannot be used. This separates the exact calculation from the practical engineering decision to order whole trucks. The code checks the data types of the rounded volume and the truck count to confirm the calculations produced the expected results. The rounded volume remains a floating point number, while the ceiling operation makes the truck count an integer. These checks help ensure engineering calculations stay accurate and consistent. This script calculates a concrete slab's volume and uses the precise value to estimate how many trucks are needed, including a safety margin. It rounds the volume to 2 decimal places for reporting, but rounds the truck requirement up to a whole number because partial trucks cannot be used. It then prints the volumes, truck estimates, final truck count, and data types, showing how precise calculations can be combined with clear, practical output. Absolute values. Absolute value is important in engineering because it focuses on size rather than direction or sign. In civil engineering, a negative value might show downward movement or compression. But for limits and tolerances, engineers often only need the magnitude. For example, beam deflection or elevation error is checked by how far it is from the target, not which direction it goes. Absolute value turns signed measurements into non-negative distances for clear error and safety checks. When using absolute values, remember what kind of number you started with and what the sign meant. Integers, decimals, and calculated results may need different rounding or reporting, and a negative or positive sign can show whether a reading is below or above expectations. Keep signed values when direction matters, and use absolute values when you only need the size of the difference, or whether it meets a tolerance. Absolute values are useful in engineering when the size of a difference matters more than its direction, such as checking whether structural movement or measurement variation exceeds an allowed limit. They support clear quality control and pass or fail decisions by focusing on magnitude. However, negative signs should not be removed without thought, because they may reveal calculation errors or important directional information. Use absolute values only when the original sign is not meaningful to the decision. Python code, absolute values. Absolute value helps keep engineering magnitudes clear, while signs still show important direction information. Data types also matter because they influence how calculations are understood and interpreted. Store the measured beam deflection in millimeters using a negative value to show direction. Then, define the allowable deflection limit, also in millimeters, as the maximum acceptable deflection. These two values are used to decide whether the beam's actual deflection stays within the permitted range. Take the absolute value of the measured deflection to get its magnitude, which shows the size of the deflection without direction. Then compare that magnitude with the allowable limit to determine whether the deflection is acceptable. Set the planned elevation for the point to 102.35 meters and the surveyed elevation to 102.18 meters. These stored values allow the planned and measured heights to be compared later to identify any elevation difference. Calculate the elevation error by subtracting the design elevation from the surveyed elevation. Then take the absolute value to measure only the size of the deviation, regardless of whether the surveyed point is above or below the design level. The output shows the measured deflection, its absolute magnitude, and the allowable limit, along with their data types. This verifies that the values are in the expected form for comparison. It then reports a Boolean result showing whether the deflection stays within the allowed limit. Report both the signed and absolute elevation error, rounded to 3 decimal places. The signed error shows the difference between surveyed and design elevations, including direction, while the absolute error shows only the size of the discrepancy. The specified protective cover is set to 50 millimeters, while the measured cover on site is 46 millimeters. These values are used to compare the intended and actual thickness and determine whether the cover meets the design requirements. Calculate the sign deviation by subtracting the specified concrete cover from the measured cover, showing whether the cover is above or below the requirement. Then take the absolute value to find only the size of the difference, which is what matters for checking compliance. The code reports the size of the concrete cover deviation as a compliance check. It ignores whether the cover is too high or too low, focusing only on how large the error is compared with the acceptable limit. This script shows how absolute values help evaluate engineering measurements against limits. It checks whether beam deflection stays within an allowable range, compares surveyed and design elevations using both signed and absolute error, and measures concrete cover deviation from its specified value. The main idea is that magnitude determines compliance, while the signed value still helps indicate direction or context. Type-safe calculations. Type-safe calculations require attention to both a value and its data type. In Python, numbers, text, and logical values are different, even when they appear similar. A beam length stored as text must be converted before it can be used in calculations. In civil engineering, checking types helps ensure data from surveys, user input, and other sources is computed correctly and matches the intended engineering meaning. Python's built-in functions help keep calculations safe by checking and converting data to the right type. This is especially important when input from forms or files arrives as text, even if it represents numbers. Use integers for counts and decimals for measurements, so calculations stay precise and match the real-world meaning of the data. Type-safe thinking helps prevent hidden errors by making sure data is in the right form before calculations or comparisons. Values like currency amounts, missing measurements, or text-based readings may need cleaning or conversion first. In engineering, careful type checks and appropriate built-in functions support safer, more reliable, and more accurate programs. Python code. Type-safe calculations. Type checks help protect engineering calculations by making sure data is in the right form before it is used. Text readings often need to be converted into numeric types, and built-in tools can help identify and fix type issues. Measurements are first stored as text because imported data, such as file contents or user input, often represents numbers this way. The span, width, and depth values begin as strings and can be converted to numbers later for calculations. Keeping them as text at first helps maintain type safety and allows conversion errors to be handled separately. The code checks the data type of a text value that represents a number. It uses the type function and prints the result to confirm the value is a string before any conversion or calculation is done. The span, width, and depth measurements are converted from text into floating point numbers. This changes the values into a numeric format, so they can be used accurately in arithmetic calculations. The calculation first converts width and depth from inches to feet, so all measurements use the same unit as the span. It then multiplies the span, converted width, and converted depth to find the total volume in cubic feet. The bolt count is first stored as text, which is common when values come from input or a file. It is then converted to an integer using the integer conversion function, so the program can use it in calculations or comparisons. The results are cleaned up and summarized for readability. The concrete volume is rounded to 3 decimal places, and the converted data types are checked to confirm that the span is a floating point number and the bolt count is an integer. The final output reports the rounded concrete volume in cubic feet along with the number of anchor bolts. This script shows how to make engineering calculations type-safe by converting text measurements into numbers before using them. It changes span, width, and depth into floating point values, converts inches to feet where needed, and calculates volume in cubic feet. It also converts a text bolt count into an integer, then prints the converted data types along with the rounded volume and bolt count for clear, reliable output. In this lecture, you learned to create variables that represent civil engineering quantities with meaningful names, use arithmetic expressions and built-in functions to compute engineering values, and applied basic type awareness to avoid common calculation errors. In the next lecture, Lecture C, we will go over strings and input. Thank you for your attention. See you all in the next lecture.